In today's video, we are talking about a very fascinating topic called number theory. And number theory is the study of integers. As I like to say it, it's the theory of numbers, or the study of numbers in it of themselves. And I have chosen to lay out a order that I have devised. It's the second edition, and I'm constantly tweaking it. The order I think one should go if they want to take a linear approach to studying math. So number theory actually ranks quite high up there, higher than most academic and educational institutions teach it. They usually teach it later in undergrad, I believe, for a mathematics major. And so I have chosen to put it higher. And I think it is in line with my philosophy that math should be taught much differently, with a focus and emphasis on logic and proofs and not on calculations and computations. And so number theory is a fascinating topic, and it was a lot of the theorems in number theory, while interesting, actually don't have much application at all. If many or all of the theorems in number theory were to disappear tomorrow, I believe, and many believe, society would still continue to trek along as it has been and will do so. But nonetheless, the ideas are still useful to think about. And Pierre de Fermat, a great mathematician in the 17th century, was thinking about number theory. And he actually wrote a conjecture about Diophantine equations. And that conjecture was that he had a proof for the solution to Diophantine equations, and that there is no solution using integers for a Diophantine equation. And if you don't know what a Diophantine equation is, you are about to x cubed plus y cubed equals z cubed. Or another way to think about it, x to the n power plus y to the n power is equal to z to the n power, where n is greater than or equal to 3. Because if it was 2, that is the Pythagorean theorem, which we know has infinitely many solutions. And if 1, it would just be the x, y, z integers themselves. And then 0 makes them trivial. So Fermat said he had a proof, and he wrote it in a book, in the margin of a book, that he had the proof for Diophantine equations where n is greater than or equal to 3. And that proof said that there is no solutions. But evidence, or the proof itself, did not exist. We lost. If it was written at all, we had no access to it. And for 300 plus years, mathematicians were trying to find proof that this in fact has, this in fact has no solutions. But then a man named Andrew Wiles came along in the late 90s, and he dedicated his life to finding this proof, or a proof for this very situation, and he was successful at doing so. And his story is really fascinating, and it's kind of awesome to think about and read about what Andrew Wiles did, because he did so in a time period that is so close to when we live now, whereas Pierre and many great mathematicians lived very, very long ago. But he did it in the 90s when I was a small child, and discovered the proof for this situation, which is called the modularity theorem. Modularity theorem. And Andrew did not do this alone. He worked with many other great mathematicians, which is important, I think, to emphasize that he is not brilliant. He just dedicated his life. Mathematicians aren't all brilliant. They dedicate their life to the challenge of solving mathematical proofs, writing mathematical proofs off work of other mathematicians that dedicated their lives to finding mathematical proofs. And we are all a community that work together to discover new knowledge. And I really want that to be the emphasis in academia, in mathematics, in physics, chemistry, biology, computer science, astronomy, whatever it is. We are a community working together to improve the quality and knowledge of the human race. With that, let's jump into some of the rest of the video, which is I'm going to go through. The cool thing about number theory is we don't have to learn a bunch of new notation. Up to this point, you have most likely been exposed to the notation that we will go through, so that will be much shorter than some of the other videos. In addition, we will go through the different number types that number theory is concerned with, focused on integers, of course. We will briefly touch on modular arithmetic and congruency with integers, and then I will focus on a fascinating topic, which is different number bases, and specifically we will focus on the duodecimal system. So with that, let's jump right into it. So the notation we need to know to understand number theory is A divides B. And it is not correct to think about this as a fraction, because this actually can have no solution. And that would be written as A does not divide B. A does not divide B. Where as a fraction, you can have any A over any B, and it would still just be a rational number. And so A divides B. A is called the divisor, and B the multiple. And it has to be a multiple of A. Otherwise, A does not divide B. And so if we use numbers, we can think about 2 dividing into 6. This is true because 2 divides into 6 3 times, and 6 is a multiple of 2. And so this equals 3 parts. 2 divides 6 3 times. An example where this is not the case would be 4 does not divide into 2. This is not true. And there are proofs for all of this. I'm just avoiding that because I think it's simpler to just do it this way. 4 does not divide into 2 because 2 is not a multiple of 4. For one, 4 is larger than 2, and so 4 cannot be divided into 2. And so that is why 4 does not divide 2. And so this is the only new notation for the most part that you will probably be exposed to with number theory. And it is quite prevalent in number theory in all the proofs. And so from here, I want to jump into the different number classes for integers. The different number classes for integers. And one of those are, we already touched on it, are fractions. And fractions are just a ratio of 2 integers. A, B. A ratio of 2 integers. So A is an integer and B is an integer. And it's just a ratio of them. That is a fraction. And humans do not like working with fractions, believe it or not. We prefer whole numbers. We try to avoid fractions for some reason. The next class of numbers that we will deal with or concern ourselves with are prime numbers, or primes. And prime numbers are positive integers. that do not have any divisors. Any divisors other than 1 and itself. So we can think back to our new notation. Our A, if it's the smallest element of a set, is going to be a divisor, is going to be a prime number, potentially. And so a prime is a positive integer that does not have any divisors. It has no A other than 1 and itself. For example, 7. Nothing divides into 7 other than 1 and 7. So this is a prime number. Another class of numbers, and let's move over here. Another class of numbers. Let's do orange. I never do orange. Another class of numbers are the composites. A composite number is just every other positive integer that is not prime. A positive integer that is not prime. Another class is just 1. 1 is itself a class. The number 1 is itself a class, and that class is called the unit. That is the word we have assigned to the number 1. We are calling it a unit. 5. Another class of numbers are called amicable numbers. And amicable numbers are numbers that have some unique relationship. An integer that has a unique relationship with another integer that can't be cleanly proven, that relationship. In other words, amicable numbers like 220 and 284 have an amicable relationship because they show a unique interaction with one another. But that unique interaction doesn't have a clean proof that explains that relationship. And in fact, maybe that theorem out there is just waiting to be discovered by you. No clean theorem explaining the relationship. And the last class of numbers I will touch on that relates to number theory are called perfect numbers. Perfect numbers are the sum of its positive divisors. Meaning that a perfect number will be the sum of its positive divisors. Will be the sum of its positive divisors. For example, the positive divisors of 6 are 1, 2, and 3. And if we add these up, we get 6 itself. So 1 is a divisor of 6. 2 is a divisor of 6. It goes into it 3 times. So 6 is a multiple of 2, and 6 is a multiple of 3, and 3 goes into 6 2 times. And so this is a perfect number. And the interesting thing about perfect numbers are they're all even. They are all even. There may be a odd perfect number, but we have not discovered it yet. And maybe you will discover it. Who knows? But it will be very, very large, and it has to satisfy a set of conditions, a set of many conditions for it to be an odd perfect number. And so these are the different classes of numbers in number theory that are fascinating. And so from here, I actually want to do a proof. I want to do a quick proof on prime numbers, which is going to be interesting. I will show you a proof on prime numbers. So let's do that. And so I wanted to prove that there are an infinite number of primes. And I've already written everything out because I did it all real time, but it took way too long, and I don't want you guys to wait for me to write everything out. So we're going to prove that there are an infinite number of primes. First, we have 2 axioms, axiom 1 and 2. The first one just defines primes as a positive integer whose only divisors are 1 and itself. Axiom 2, for every integer n, where n is greater than 1, is divisible by a prime. Now, in order to prove that there are an infinite number of primes, we can assume, let's try to assume that there are only a finite number of primes. So consider a set of divisors of n, and n can be any integer. N can be any integer. It's bothering me that there's no n parenthesis here. N can be any integer. So this set of divisors, we'll call it set A, has an element represented by x here, where x is a divisor of n, and x is greater than 1 but less than n. So that is our set. Now this set can either be empty or not empty. If the set is empty, by definition it would be a prime. Why would it be a prime? Because an empty set means that x does not satisfy these conditions. No element in x is a divisor of n and greater than 1 but less than n. And so if that is the case, it is by definition a prime, because primes are positive integers whose only divisors are 1 in itself. So x is 1 or n. That's number 1. What if the set is not empty, so it has elements? Then A has the smallest element, and we could call it D. So set A has the smallest element, we're calling it D. If D has a divisor, D would be greater than 1 but less than n. Then n would also have a divisor too, right? N would have a divisor too. But this is impossible because we've defined D as the smallest divisor. D has no divisors. D is prime, and it's either 1, and it is 1. It can only be 1. And so if D is prime and n has D as its prime divisor, it is impossible to have another divisor. So if we assume there are a finite number of primes, we reach a point in the mathematical logic where we must divide into 1. The only possibility if the set is not empty is 1. And we can't divide into 1. For every integer n, which is because of our axiom 2, for every integer n is greater than 1, is divisible by a prime. But it says nothing about n if it is 1. So we can't divide into 1 because it's already been proven to be impossible. And no primes divide 1 because all are greater than 1. Axiom 2. All for every integer n is divisible by a prime. For n is greater than 1. So no primes divide 1 because all are greater than 1. And so this is a proof by contradiction. This is a proof. Let's write that out. Proof by contradiction. By assuming the contradictory response that there is a finite number of primes and proving that that's impossible, we have proved that there is an infinite number of primes. And as of November 22nd, the largest or the greatest, the highest prime number we have discovered is 2 to the 82,589,933 minus 1. That is the highest prime we have calculated or computed. But since there's an infinite number of 1, it goes on forever. And so this is the proof for there are an infinite number of primes. This explanation is way quicker than when I first did it and I was writing everything out, which I also recorded, but I'm not putting up because I think that alone was 20 minutes. And so with that, we'll wrap up this video. I actually will do the duodecimal system as a standalone video because I find it so fascinating. And so with that, I will see you in the next video. See ya.